Hello, everybody. This is a re-recording of the Repeated Measures ANOVA lecture. This is actually the third one I'm doing, so I've wasted 3 hours because of some sort of sound problem, which I think is due to the microphone. So if you hear a little bit of tiredness in my voice, that's probably why. So let's hope that this one goes well, because I can't tell during the recording if there's any audio problems. I only tell after the fact, which means after there's an hour and a half wasted. And I don't want to break this into parts because I think that makes it difficult for you guys. So repeated measures, ANOVA, is the second type of ANOVA that we're going to talk about in the class. We talked about one-way ANOVA. A one-way ANOVA is very similar to an independent t-test in that we have a between subjects design. So in between subjects design, each person gets exposed to just one level of the IV. So if we take the independent t-test, then if we want to see if red leads to more attraction, we can have a red group and a blue group. So half our people see red and they rate the attraction. Half the people see blue and they rate the attraction. And we compare those two independent separate group means to see if there's a difference. In ANOVA, the one-way ANOVA, we have 3 or more levels. So let's just say we have 3 levels. So we have red, green, and blue. So 1/3 of our people will see red, 1/3 will see blue, 1/3 will see green, and then they'll rate the attraction of the person. So we have 3 separate groups in the one-way ANOVA. And we're going to ask whether those groups are different in their attraction. And we only measure attraction once per person. And then in repeated measures ANOVA, it's very similar to the paired t-test in that it has a within subjects design. So within subjects design, everybody gets all levels of the IV. And so in the paired t-test, we're comparing 2 things. So we could compare red versus green. So each person is going to get red, rate the attraction, and then they're going to get the green, rate the attraction. So they have 2 scores. They at every level of the IV, they rate the attraction. So they get a score on the DV for every level. And then what we did in the paired t-test is we compared those 2 scores within people. So we get the different scores. So for every person, what was their red score versus their green score? And so the repeated measures is similar in that we have the within subjects design. So everybody's going to get all levels of the IV. So if we have red, green, and blue, they're going to see red, rate the attraction, green, rate the attraction, and blue, rate the attraction. And then we're going to ask whether there's a difference, some difference among those color conditions within people in the repeated measures ANOVA. And essentially, we would do this repeated measures ANOVA. There could be 2 different scenarios. One is we could have the thing be an IV. So just like what I talked about with the colors. So we could have red, green, and blue. So it's an independent variable, and we're manipulating that, and we're presenting those different colors to our participants to see if it affects their attraction ratings. So the other condition is in a non-experimental study. So if we're just basically, the big way that we would do this is comparing people over time. So I think the best example here is the therapy. Let's say that we're curious if our therapy will help people be less depressed. So we measure people's depression before they start the therapy. Then we might measure their depression immediately after they finish the therapy. And then we measure their depression 6 months later. And so we're measuring the same person's level of depression over those 3 periods of time to see if the therapy made a difference. And so basically in either one of these designs, whether it's an IV or whether we're repeatedly measuring people over time to see if they change, the big key to this design is that we're measuring the same people several times on the dependent variable. And so The hypothesis that we have is very much the same like our one-way ANOVA. Our hypotheses are very vague, I think, in the statistical ones. So the statistical hypotheses are just essentially that the HO is that there's no difference among the conditions. So your level of attraction for red and blue and green are going to be the same. And then the alternative hypothesis is that there's some difference. So it's not specifically, it just says there's some difference. So the F is just testing, is there some difference among those colors? It doesn't tell us any direction or which colors are different. It just says there's some difference. And so I'm going to actually talk a little bit here about what this thing is doing. I'm just kind of curious what's going on here. Yeah, what this thing is doing. I'm just praying that this recording works, because if this doesn't work, I would have spent 4.5 hours for no reason. And so I'm not very happy about that. So let me snip this thing so I can draw on it to say what's going on. And so we're going to compare the two ANOVAs that we had so far. So we have the one-way. Again, I'm writing on this small little laptop pad here, so it's a little bit hard. So it's between subjects design. So we have each participant getting just one level of the IV. They see red or green or blue, so we have different groups. Then we have the repeated measures ANOVA, which is within subjects. So everybody gets all levels of the IV. So you see red, you rate the attraction. You see blue, you rate the attraction. You see green, you rate the attraction. And so remember, in one-way ANOVA, we're partitioning the variance. And so in our little study we're talking about, we can find out everybody's attraction scores and then see how they differ. And that's the sum of squares total. And then we're just simply dividing up the variance here. And I don't know if I like how I did that. I don't really like what I did. So I'm going to erase this line if I can. Oops. I don't erase a link. Oh, great. It's actually making me do that. That's fantastic. So, starting again. So we have the one-way. That's between subjects. We have the repeated measures. That's the within subjects. And then the one-way, if you remember, we're partitioning the variance. So we have the sum of squares total. So that's all of the variance that people show in their attraction ratings. And we're just simply dividing it into two pieces. So we have the between, which is the stuff that's directly linked to the IV. So how the color affected the attraction scores. So we know what's going on. It's something to do with the color because the groups are different. And then we have the within. And here we don't know what's going on. It's just the stuff that's left over. We're not sure why people are different. We just know they're differing for some reason. They're differing from their average of their group, but we don't know why, and we don't know exactly what's going on. It's unknown. And so then our F was just between divided by within. And so repeated measures is different in some ways, but we always are going to start the same way. We're going to start with this sum of squares total. And conceptually and mathematically, in terms of the formula, it's exactly the same as the one-way. And then we're going to have a between. We're going to specify it's between treatments. So here we say between treatments. But again, treatments is the IV, so it still is the effect of the dv by the iv. And so, again, just like the sum of squares total, this is conceptually and also mathematically in the formula the same. And then in the repeated measures, we are going to find the within. The within is here. So the old within is still the same. It's this other stuff on the right side of the line. So that within is the same. But we're going to do something different in the repeated measures. So here we can actually take a piece out of the old within. Because remember, the old within, we had these big question marks. We don't know what's going on here. Because we've repeatedly measured people on the dependent variable. So now we know whether people are high on the dependent variable or low or in the middle in general. You know, if we just look across the conditions, not paying attention with the conditions per se, but we can know if somebody's picky, they give low scores on the attraction in general, or somebody's relatively not picky, they give high scores, or if they're in the middle. We know that now because we repeatedly measured them on the DV. We know their general tendencies. So we can actually identify the variance, the sum of squares, between subjects. So between subjects. Between subjects, and this is simply, we can just call this individual differences. Individual differences. So some people are high in general, some people are low in general, some people are in the middle in general. Some people are picky, some people are not picky, some people are in the middle. So now we know this stuff. So we've carved out a piece of the unknown, the great unknown of the within. So now we actually know what's going on here. We know that there's something about the people that they're just different. We might not know exactly how. We don't know exactly if they're picky or there's some other things that are going on, but they're just different. And now we know this stuff. And so now the question marks about what we don't know is now smaller. We've taken this piece here. And so this is actually called error. So in repeated measures ANOVA, we start the same. We find the sum of squares total, sum of squares between treatments, BT, and sum of squares within. We find that. See, we already have those parts. We find those things. The only thing that's new is essentially we find this. We get to calculate this because we've repeatedly measured people, so we can find out if they're high or low in general on the DV. And then what we do is we take this within, we subtract this between subjects, and we end up with error. And that error is lower than the within. So you can see the size of the error is smaller because we've carved out this between subject stuff. So the error goes down. And the error is what we put in the bottom of our F formula. So our F formula is still going to be the between subjects on top, I'm sorry, between treatments on top, the effect of the IV on top. But on the bottom, we're going to have this smaller error. And it's smaller because we've now identified the individual differences with the repeated measures, and our F should go up because of that. So this is essentially the new stuff, is that we identify this. So this is a new thing. So we take the old within, subtract the between subjects to get the new error. That's essentially what's new with the repeated measures ANOVA. And so that's what this is talking about. So now we can identify if people are high, low, medium on the DV, picky, not picky, average. And that's the only change. And so the first stage of the repeated measures ANOVA is exactly the same as the one way. We find the sum of squares total, sum of squares between treatments, and sum of squares within. The new stuff is we find the sum of squares between subjects, so the individual differences, are you high, low, in the middle in general on the DV. We subtract that from the old within treatments, and we get this new thing called the sum of squares error, that smaller little chunk that then becomes the bottom part of the F formula. So I'm going to go really fast through the stuff that's the same because we're going to use the same data as we did for the one-way ANOVA. So I'm not going to go into details about that because there's a lot of details in the last lecture. So the formulas, you can stop this if you want to, but the formulas for this first step is the same as the one-way ANOVA. SS total, SS within, SS between treatments, the same formula. The new stuff is the SS between subjects, so those individual differences. Do notice the last part of the equation is the same as what we had before. For total, G squared over capital N. Between treatments, G squared over capital N. We still have that. The only thing that's new is we're going to take this part of the formula. Well, what is this? What is P? So P is really simple. So P is, we're just going to add the scores for each person across the conditions. So in the study I've been talking about, so each person has a red score, each person has a green score, each person has a blue score. So for every person, so person number 1, add their red plus their green plus their blue. That is P. Take person number 2, add red plus blue plus green. That's P. And once we've added those together, we just simply square that number. So let's say it's 2 plus 2 plus 2. My P is 6. So 6 times 6 is 36. So P squared would be 36 for me. And then, well, what do we do here? Well, K is the number of conditions. So there's 3 colors. 3 colors, 3K. So 36 is my P squared divided by 3. Voila. 12 is this ratio for me. So you're going to do that for every person. Find this ratio, and you're going to add it together. Don't worry if you're not quite catching this. We'll have data, and we'll actually show you how to do that. And then the second step we have to do with the sum of squares is we have the sum of squares between subjects now. We take the old within, and we subtract the new sum of squares between to find the new sum of squares error, the smaller little chunk that I showed you in that drawing. We also have to figure out the degrees of freedom. There's a few new things. Some are same. Degrees of freedom total is the same. Just remember in a within subjects, capital N is the total number of measurements of the DV. So let's say that we have 7 people in our study and we show them red, green, and blue. And so our N, capital N, would be, we have 7 people, we've measured them 3 times, so we have 21 measurements of the dependent variable. So 21 is our N. So our degrees of freedom total would be 21 minus 1, it'd be 20. The second thing is new in some ways. It's the degrees of freedom within treatments. It's the degrees of freedom within each treatment. Each treatment is our level, so red, green, blue. So within each, how many degrees of freedom do we have? Well, it's minus 1. So red, I have 7 people, 7 scores. 7 minus 1, it's 6. Blue, 7 minus 1 is 6. Green, 7 minus 1 is 6. So 6 plus 6 plus 6, 18 degrees of freedom within treatments. Between treatments is the same, so it's K minus 1. So 3 colors, 3 minus 1, 2 degrees of freedom between treatments. And so in this case, this can, in the real world, this can vary. In this class, it's always going to be 2 because I don't want to make you do a lot of extra work when there is more than 3 treatments. 3 levels is enough to calculate. And so we're always going to have 3 minus 1. So it's going to be 2 for us all the time in this class, in homeworks and on the exam. And then we have a degrees of freedom between subjects. I should say for hand calculations, we might have a ANOVA summary table that you fill in the pieces, which is really quick and you're not computing a lot of stuff. That might be different. But in terms of long problems, it's always going to be 3 minus 1. Degrees of freedom between subjects. So here we have a small n minus 1. What's small n? Well, how many scores do we have for each color, each condition? Well, I said we had 7 people, so we have 7 scores for each color. So between subjects, 7 minus 1 is 6. Degrees of freedom error. Error is always going to be just like our sum of squares error, within minus between subjects. Within minus between subjects. So degrees of freedom within minus degrees of freedom between subjects. So our within in this case was 18, and our between subjects was 6, so it should be 12 degrees of freedom error in our example. Or you could do k minus 1 times n minus 1. So k minus 1 is 3 minus 1, n minus 1 is 7 minus 1. So this is 2, 3 minus 1 is 2, 7 minus 1 is 6, 2 times 6 is 12. So it comes up with the same number. You can do one or the other solutions. You don't need to do both unless you want to double check things. And so now we have our last step in terms of finding the F's. So the mean squares between treatments is going to be the same as the one-way ANOVA. So we're going to take sum of squares between treatments divided by degrees of freedom between treatments. And again, that number is the same as from our one-way ANOVA. What's different is our MS error should be smaller. And so MS error is sum of squares error divided by degrees of freedom error. So sum of squares divided by degrees of freedom. And then once we have that, then we solve our F by having mean squares between treatments divided by mean squares error. And so now we calculate the effect size. That's our last calculations. And so here, what we're going to be doing is we're going to just basically do the formula here. There's two formulas. You can do one or the other. I don't really need to explain these formulas. You're just going to plug in the numbers. There's nothing really conceptual that I'm going to talk about here. So do one or the other formula, and we'll do this with some numbers in a second. And the partial eta square interpretation is the same as the eta square from the one-way ANOVA. Okay, let's do the first example. So the first example, what I've done is I've taken the same data as we had for the example in the one-way ANOVA. I've just converted it to within subjects design. So you can go ahead and look if you want into the one-way ANOVA lecture PowerPoint if you want to. But this is exactly the same. We have 3 levels, placebo, low, and high. And we're seeing whether this drug affects positive emotion. And so we have these scores are exactly the same. The only thing I've changed is I've made this into a within subject. So each of these 5 people have 3 scores. And so I'm going to actually write on this a little bit. And again, I'm praying that this thing is working well and I don't have to record this again. I'm not sure what I'll do if I have to spend 7 hours recording one lecture. If that happens, maybe we'll just go to a live session, which I don't really want to do because I know that people have kids and things like that, and it might be difficult for them. So let's go ahead and look at this. So this part is exactly the same as the one-way ANOVA. I'm not going to say anything different. All I'm going to say is if you don't understand this worksheet, go back to the one-way ANOVA and look at it. It will explain how to do that. I'm also trying to make this a quicker lecture because of the technical issues, but if you really want to find this out, it's in the one-way ANOVA lecture. The only thing that's new is this stuff. So what's new is finding out P and P squared. Remember, P is we're adding for the person. So person 1, we're looking for placebo plus low dose plus high dose. That equals 15. 15 times 15, P squared is 225. We can look at person number 3, placebo, low dose, high dose. Add those together, it's 10. 10 times 10 is 100. So the only thing that we're doing new here is P and P squared. That's the only thing that we're doing that's new. So again, the N, capital N, is the total observations of the DV. So in this case, we have 5 people measured 3 times placebo, low dose, high dose. 3 times 5 is 15. So capital N is 15. By the way, capital N was 15 also for the other study in our one-way ANOVA using the same data. We just had 3 groups of 10 people. I'm sorry, 3 groups of 5 people. So 15 is the same. So what I'm going to say about this, and I kind of hate saying this, but there is a very detailed explanation of this first step of the repeated measures because I'm using the same data. So the sum of squares total is the same from the one-way. So if you don't understand this, please watch the first lecture, the one-way ANOVA. It will explain this in detail. Same thing for the within. We're just getting it from the worksheet, by the way. So the worksheet was up here. So we're just plugging these numbers in from the worksheet, and I explained this in big detail in the first lecture, and also for this. So the between treatments, sum of squares is exactly the same as for the one-way ANOVA. You can double check this. Go back to your PowerPoint for the one-way ANOVA and check these slides. The numbers are exactly the same. So that first step is the same. First step is the same. Sum of squares total, sum of squares within, sum of squares between treatments. These numbers are the same. They add up. Between, within, total. Between plus within equals total. The only thing that's different, that's new, is that we're doing the sum of squares between subjects here. So here, if you remember from our worksheet, we have the p squares. And so for each person, we're going to take p squared divided by k. So I'm just going to show you where the p square is. The p square is right here. So for each of the 5 people, we have p squared, and we talked about how we got that earlier. So we have the p squares here. So all we're going to do is, for every person, we're going to take their p squared divided by k. K is the number of conditions. We have 3 drug conditions, placebo, low dose, high dose. And so for each person, we're going to take that ratio, and then we're going to add everybody's scores together. So person 1, here's their p was 15. So this is placebo, low dose, high dose. P was 15. 15 times 15 is 25. So 225, I'm sorry. P squared is divided by 3, k. There's 3 conditions. So that ratio of p squared divided by k for person number 1 is this. Person 3, if you remember, we looked at this. The placebo, low dose, high dose. We add those together, the p is 10. P squared is 10 times 10, 100. So p squared, 100, divided by k is 3. So 33.33. So we do this for each of the 5 people. We add these things together. We add these together. It comes up to 197.99. I rounded it up to 198 because we have some rounding errors here with these 0.33s. So we have the between subjects first part. We have the sum of p squared divided by k. Now we're just going to take this, g squared divided by n, which we solved before in the previous problems. And so our g squared was 2704, and we divided it by n, which was 15. And so in the one-way ANOVA, you can go back, you can see that we solved this. So 198, which was sum of p squared over k, subtract g squared over capital N. So our sum of squares between subjects is 17.73. So between subjects, 17.73, that's the new stuff. We're going to subtract that from the old sum of squares within, which is the same as the one-way ANOVA. So that old within minus the new sum of squares between subjects, we get the new sum of squares error. And so we also need to calculate the degrees of freedom. And so this is the same as the one-way. We have 3 drug conditions. We have 5 people. So 3 times 5, we have 15 measures of the DV. 15 minus 1 is 14. The within treatments, degrees of freedom inside each of the treatments, we have 5 people. We have 5 measures of the placebo. We have 5 measures in the low, and we have 5 measures in the high dose. So in each treatment, we have a degrees of freedom of 5 minus 1. 5 minus 1 is 4. 4 times 3 treatment levels is 12. So 4 in placebo, we have 4 in low, and we have 4 in high. 4 plus 4 plus 4 is 12. The between treatments is the same as the one-way ANOVA. 3 minus 1 is 2. And then the between subjects, which is new, it's the low n minus 1. Well, low n is how many scores do you have in each of the levels. So we have 5 scores in each of the levels. So 5 minus 1 is 4. And then we have the error. So error is always going to be within minus between subjects. So within minus between subjects, within minus between subjects in terms of degrees of freedom. So 12 was the within, and then 4 was between subjects. 12 minus 4 is 8. Alternatively, you could take k minus 1 times n minus 1. K minus 1 is 3 minus 1. N minus 1, and small n is a number of scores in each level. So that's 5 minus 1. So that's 2 times 4. 2 times 4 is 8. So you only have to do one of these unless you want to double check, but both of them come up with the same number. The mean square, so now we can do the mean squares since we have the degrees of freedom, and we only need mean squares between treatments and mean squares for error, because that's what we need for the F. So the between treatments is the exact same number as our one-way ANOVA. So to get the mean squares, we do sum of squares divided by degrees of freedom. You can double check with the one-way. This is the same. This does not change. The effect of the IV is the same. Mean squares error, it's the new one. So we take our new sum of squares error divided by our new degrees of freedom of error. We just plug in the numbers and we get the mean square error. And again, our F is the mean squares between treatments. That's the same as before, but now on the bottom, it's mean squares error. Our question mark is smaller. So the stuff that's left over is smaller because we took out the individual differences with the between subjects. So we do the MS error on the bottom. So we go ahead and calculate this. We plug in the numbers, and our F is 13.71. Remember that our degrees of freedom between treatments and error is 2 and 8. Between treatments, error, so 2 and 8. So we go to the table, we go to column 2, and we go to row 8. And so, oops. So we go to column 2, we go to row 8, and we get 4.459. I'm going to round it up to 4.46. And so our calculated F is greater than the value in the table, and that means we reject the HO. So we reject the HO. There is an effect of the drug on positive emotion. You do the effect size, you do only one formula. So we just plug in these numbers. Between treatments, total. Between subjects, just plug in the numbers that we calculated. We remember our order of operations. We subtract this first. Then we take this ratio, it's 0.77, so it's large. Or you can use this formula, which is a little bit easier. It's got the same number between treatments plus error. So between treatments, plug it in, same number here, and plus error. And voila, you add this first in order of operations. You get 26, which is the same as that. And we get the same number, of course. It's 0.77. So do one formula or the other. You don't need to do both. Again, this is a large effect size. So we write it up, and it's very similar to the one-way ANOVA. So we have a table 1 with our descriptives. And then we have our ANOVA table. The difference in this ANOVA table is I've removed the total. I don't want you to do the total because I'm afraid that you'll think that all of these 4 things add to the total. They don't. This between treatments plus within equals our total. But I don't want you worrying about that, so just drop the total. By the way, this part is the same as the old one. You can double check it with the one-way ANOVA lecture. So the stuff for the between treatments and the within is the same, including the MS, the mean squares for between treatments. What's new is that we have our old within, we found our between subjects sum of squares. So we took the within, subtracted the between subjects to get the error. Same thing for degrees of freedom. Within, subtract the between subjects, we end up with the error. And then remember on the bottom of our F, is mean square error. So we take the sum of squares error sum of squares error divided by degrees of freedom error. We find the MS error. So to find the F, we take the mean squares between treatments divided by mean squares error. We get an F of 13.71. That's what we calculated, and it was significant at the 0.05 level. Because remember, our alpha is 0.05. We put a little star because we rejected the HO. There is an effect. So we refer to the tables in the first sentence. And this sentence is the next sentence is very similar to the one-way ANOVA. So positive affect. So the DV was influenced by the dosage of the drug. So in this sentence, we're just saying if there is a significant relationship between the two. But we can't say what the direction is because we don't know the groups, or I'm sorry, the levels of the drug, which one affects it from the F. It's just that something's going on. So something's going on with the drug affecting the positive emotion. Give our F information, we give our degrees of freedom. Between treatments, we give our degrees of freedom error, and we get our F that we calculated. And P is less than 0.05. It's saying that we rejected the HO, and our probability of making a type 1 error is less than 5%. And so we need to be honest. We need to say that post-hocs are needed to determine the specific differences between the dosage conditions. However, if we look here at the descriptive table, it looks like high dose has higher positive affect versus the other two. And by the way, this should look pretty familiar from the ANOVA, the one-way ANOVA. And the effect size was large, partial eta squared equals 0.77. That's what we calculated. So just to remind you is that the F here, just like the F for the one-way ANOVA, is a protected test. So there's two stages. We do the overall F. And if the F is significant, meaning we reject the HO, there is some difference among the levels, then we can dig into the post-hocs. And then conversely, if the F is not significant, we fail to reject the HO. We can't go any further because if we start digging into the pieces, we could make a type 1 error. So we don't do that. And if you did the one-way ANOVA SPSS lab, you saw that we used the Tukey for that. Tukey is a good method. And then our assumptions are very much the same. And these are repeats except for the last one. So these are the same for the one as the one-way ANOVA, except for the last one. And the last one is sphericity, and it's best to show you what's going on. So remember, we're doing repeated measures. So we're doing comparisons for each person. So these are people. This is 6 people in the study, and they're being measured at time 1 on some sort of dependent variable, time 2, and time 3. So we're kind of curious if there's some differences here. So in terms of sphericity, what we do is we figure out the difference scores. So 1 minus 2. 1 minus 2 is -5. 1 minus 2 is -4. And then we figure out the difference between 1 and 3. So 42 minus 43 is -3. So we do that for every person. And then we compare 2 and 3. So 455 minus 59 is -4. So these scores are just 1 minus 2, 1 minus 3, 2 minus 3. Now these scores are considered raw data. We can actually put these scores in our online calculator and find out the variance. Same thing for this. Put those scores, find out the variance. Put those scores, find out the variance. So what sphericity is saying is that those different scores, their variance should be relatively the same. So if I'm looking at these two, they're pretty close. I wouldn't be worried about the sphericity stuff. However, here, 3.1 is way off from these other two. So this is probably a violation of sphericity, and you'd have to do some adjustments in the repeated measures. So I just want you to know what sphericity is in terms of the concept here. You don't need to actually do it or test it. And so real quickly, remember that our advantages of repeated measures design is similar as the within subjects design that we talked about before. Basically, we can now measure individual differences. So we can tell whether somebody's picky or not picky or in the middle. So that allows us to reduce the error. So when we reduce the error, as we saw in our formulas, we should be able to find a more significant F, we hope. There should be more power. And then we did less people. So if you remember when we did a between subjects design and we needed 30 pieces of data with, three levels. So if we wanted like red, green, blue, and we wanted to get at least 30 measures of those combined, we'd have to get 3 times 10. We would need 30 people. We'd actually, because people are just measured once. So there had to be 30 people. In the within subjects design, we can literally just have 10. We get 10 people, we measure them 3 times, so we got 30 pieces of data. So we need less people to get the same amount of data. Disadvantages is the same. The first thing here is what we're talking about over time. Remember about the depression. So we measure depression before therapy, then initially right after therapy is done. By therapy, we mean like, probably at least 3 months of therapy. And then you get out of therapy and you measure it 6 months later. Well, maybe 9 months or maybe 18 months or maybe 2 years passes. Maybe there definitely could be things that happen to the person that affect the depression scores that aren't part of the IV. So it could be hard to interpret the data. Also within subjects, you could have a practice effect. So if it's a task, let's say you're trying to solve a problem, well, the more times that you do it, because remember, repeated measures, you have to keep on getting the measure of the thing, you might get better, so your scores improve. But it improves because you're getting practice, not because the IV is making you do anything different. Experience can change your scores. So in the attraction, I'm doing the red and the green and the blue. So the first time I do it, I'm not really sure what I'm supposed to do, or I'm not sure what I'm supposed to be looking at. I'm not sure what the photos are, and I'm a little bit general when I'm doing. And then the second time, I thought, oh, the photos are like this. I need to look at the eyes. I need to look at the nose. And then this, third time, I get really specific. So I might change my attraction ratings just based on having some experience rating the attraction of other people. And then fatigue might also set in. So let's say you have people repeat a task, so you have them do something over and over again, and they're like, ugh, I'm sick of it. So their performance might go down because they're getting tired. And so all three of these things, your behavior is changing, your dependent variable measure is changing, but it's not due to the IV, it's due to other things. And so that's a problem because you see people change their behavior and you think it's your IV, it's not, it's because of these things. And typically, you can usually avoid these problems with the within subjects design by having counterbalancing. So instead of everybody seeing red, green, blue, you mix it up. Red, green, blue, green, blue, green, red, green, red, blue. You mix it all up in different orders. So you do counterbalancing. So go ahead and on Canvas, there is a practice problem. And so if you go on Canvas and you go down here, right here, so there's going to be the video here, and then you have the PowerPoint, and then you're going to have the practice problem. Open this up, and you'll see that this is exactly the same data as from the one-way ANOVA. These data are the same, except now we have a within subjects. That the 3 sound conditions, everybody is exposed to each of the 3 sound conditions. So what I'll say is when you solve this, you can definitely use what you wrote for the practice problem for the one-way ANOVA. The sum of squares total, sum of squares between treatments, sum of squares within are going to be the same. So you don't need to necessarily waste your time. And your worksheet will be the same, except you're going to have to figure out the p and the p squared. So you can save time in doing this. So go ahead and solve this, and I am going to let you pause, and I'm going to go through the solution when you're done. Okay, so I'm going to go through this real quickly. So the sum of squares total. Oh, I'm going to actually show you the worksheet. Sorry about that. Oops, not here. Here it is. So the only thing new is this stuff, is the P, and I'm going to make this a little bit bigger. The rest of the worksheet is exactly the same as from the practice problem in the one-way ANOVA. So the P is new. So P is constant plus random plus no. So 7 plus 5 plus 2 is 14. 14 times 14 is 196. So constant plus random plus no for number 7, person number 7, 2 plus 2 is 5. That adds up to 9. 9 times 9 is 81. So that's P squared. So that's the only thing that's new. So the sum of squares total is exactly the same as from the one-way ANOVA lecture, and please refer to that lecture if you didn't get that. Same thing for the within, same thing for the between. Listen to the one-way ANOVA lecture if you're not sure how to do that. This thing is the same. What's new is the between subjects. So I'm going to take the P squared divided by K. K is 3. So again, there's 3 levels, the sound levels, sound conditions. And I'm just taking the P squared from here, 196, 169, 256. You can see it here, 196, 169, 256. So take that and divide it by 3. 3 sound conditions. So there's 1, 2, 3, 4, 5, 6, 7, 8 of those ratios because we have 8 people. So for each person, P squared over K. And then the G squared over N is the same as what we had in the previous sum of squares total, sum of squares between treatments. So we solve for the ratios. So solve for the ratios, there's 8 numbers here, 8 people who were doing P squared over K. Subtract the G squared over N, which is this ratio. We then add those 8 scores together, and we get 11.96 for sum of squares between subjects. So now we can find the sum of squares error. We can take the old within treatments, which we had from the one-way ANOVA. Now we're subtracting the new between subjects to get the new error. We do our degrees of freedom. Our degrees of freedom total is the same as the one-way. We have 8 people measured 3 times, so 24 measurements of the DV, 24 minus 1, 23 degrees of freedom total. Degrees of freedom within treatments is the degrees of freedom inside each of the treatment, adding them together. So we have 8 people, 8 minus 1, we have 7 degrees of freedom in each sound condition. There's 3 sound conditions, so 7 times 3 is 21. Between treatments is the same as the one-way. It's always going to be for us 3 minus 1 is 2. Between subjects is lower n minus 1. We have 8 people. 8 people minus 1 is 7. Error is always going to be within minus between subjects. So within 21 minus 7, 14. Conversely, you could do k minus 1 times n minus 1, k 3 minus 1, and small n 8 minus 1. So that's 2 times 7 is 14. Same number. You just have to do one or the other unless you want to double check. Now we can do the mean squares between. This is the same as the one-way ANOVA. Mean square is always going to be sum of squares divided by degrees of freedom. Mean squares, this is our new thing, our new sum of squares error divided the degrees of freedom error. Our mean square error is 5.42. Our F is the between treatment, so the MS between, that's the old one. And then now we have the new smaller error on the bottom. So mean square between treatments, mean square error. We come with 2.78. Remember that we have 2 and 14 degrees of freedom, 2 between treatments, 14 for error. And so I go to the table, it's 2 and 14. 2 for the column, 14 for the row, and so we have 3.7389. So I'm going to round that up to 3.74. And we don't make it. So our F that we calculated is lower, so we failed to reject. You might say, well, this is different because I believe we found barely a significant finding for this one way, and I was saying that there's more power to this because we can take out the individual differences, but it doesn't work here. And one of the reasons is because if you look at the sum of squares between treatments, It's very small. You see the within's pretty big, the between's pretty small. And then if you go to the data, which I have here, and so if you go to the data and you actually kind of compare it, I was wondering about this myself. You have somebody who's relatively okay, and then they're really low here. And then you have somebody who's pretty high, 8, and they're low over here, 1. You have a 9, and then you have a 2. There's a lot of sort of variation within people. So the individual differences didn't really stand out in these data. And so that's, I think, a big reason why our between subjects was so small, and that's why we failed to reject it here. We do the effect size, so you just plug in the numbers. Plug in the numbers, 0.28, it's large, or you plug in the numbers here. 0.28, it's large. We write it up. It's pretty short because when you have a non-significant finding, it's really short. So we have our table 1, we have our table 2. You can double check those things. And then all we say is, after we refer to the tables, we say, okay, we did a repeated measures ANOVA, and the IV did not affect the DV, not affect. So it was not significant. We give our F information, degrees of freedom between treatments, degrees of freedom error. Our F we calculated, it's not significant if we failed to reject, not significant. It's not significant, so we can't dig into these pieces. We stop right there. So we say the effect size was large, partial eta score is 0.28, and we have our tables, and that's it. So if you have any questions, join us for the live sessions. You can ask me. The homework will be due Monday night to give you a little bit, an extra day at least, to get prepared before we start reviewing for the exam early next week. And the repeated measures ANOVA is really messy in SPSS, so there is no SPSS lab for this ANOVA, repeated measures ANOVA. So there's just a homework, no lab, and I hope that this recorded well. And I'll talk to you later.